Hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We have a special guest in the studio with us who will be joining us for the rest of our streams as a trusted companion. If you have noticed, if you are an observant viewer, you may have noticed that there is now a little owl icon up in the corner here. This owl icon was generously donated by Quartertron. If you seen him around on the streams, on the IRC or on the Twitch chat as Quartertron. He sent me a pretty fabulous device a few months ago, about 2 months ago. I haven't had a chance to really play with it. I had a chance this morning to do so and make sure it was all working. And so I have it set up now. It is a notification owl that is actually a physical device. And I don't know if you can see this here on the webcam, but it's a little, I don't want to stretch the cord too far, but it's a little owl. And well, let me see if you can see that on that. Let me bring up the little window and see if you can see that here. It's really hard for me to, I can't quite, well, you know what? I can unplug him. There we go. It's a little owl. And on the back of the owl is a like USB plug. You can see it kind of has a USB butt. And if you plug this USB butt into the cable and plug it into the computer, the owl can be told to light up. And so, for example, when you first plug it in, it'll light up just to tell you it's working. But now if I go onto the stream, and I'm going to go on to the Handmade Network IRC, which is where it listens. If I talk to Owlbot and just say something, then he will, the little owl will light up. That is how this works. I don't actually know. Let's see, I should probably restart him here. There we go. All right. I don't actually know if I think only Quartertron can signal him. I did give Insobot the ability to signal him as well, and so at some point we'll have to get Insobot to be able to signal him for various reasons. Yeah, there he goes. So I don't know if you can see this again, because I think the cable doesn't quite reach as long as it might have to. Maybe I can just put it in the corner here, though. There you go. So I'm going to go ahead and try to signal him here on the IRC so you can see. Do you see how he lights up like that? That's what happens. So what that means is I will be able to see if there's a problem with the stream, like there is sometimes. We had this happen. That's why I wanted to try and get him working. We had this happen where the stream, there was a hotkey or something in OBS that made it so that my webcam took over the full size of the screen last time or something. So hopefully the Owlbot signal can be used now to signal me when there is a problem, and I trust that we can add people to the Owlbot signal OK list so that someone will always be watching and signal if there is a problem. So there you go. That is our new feathered friend, and thank you very much to Quartertron for sending that in. It's pretty awesome. I think he's kind of got this down now. I think he was saying that he now makes these guys. They're basically like little, I don't know, like bath toys or something, little or like cat toys or something that he then kind of hollows out a part in the back and puts an Arduino into. It's a pretty great idea. So yeah, you should set up a little store, notification owl store. All right, so that is our special guest, and as long as he is up here, or she, I guess I don't know the gender of this owl, but the friendly notification owl can let me know if anything weird is going down. So we are now good to go. All right, I will go ahead and get started here. Let's go ahead and open up the project. And if you remember from last week, we're actually at the part where almost everything is what we wanted it to be at a basic level. The only thing that we were unable to get working on this graphics card is apparently, for whatever reason, multi-sample rendering, which we now use. Multi-sample rendering is not available with sRGB, which makes not a whole lot of sense because those things should probably not be related, but I guess they are. I mean, I guess I could see why they might be. If you're writing to multiple samples, maybe the hardware that does the translation only works on sample 0 or something like this. If that's possible, it seems unlikely, obviously, but it's how should I know, right? I don't know how the internals of this card work. I'm definitely not in a position to say what should or should not be easy in the particular pipeline that this card implemented, because I have no idea what they implemented. But suffice to say, that means our graphics are not quite correct. So what we're looking at here is almost an exact replica of what we had before we decided to implement all the 3D stuff. But there's like all the colors are too dark, right? They're being rendered as if they have sRGB, so like the textures are in an sRGB format. The rendering is set to use sRGB, but sRGB is not available in terms of the texture to which we are rendering. And so as a result, we get incorrect results. Now, we can fix this by implementing sRGB ourselves, and maybe that's the right solution. I don't know. If we just implement sRGB ourselves, what that means is that we will square and square root our colors as they come in and out of the pipeline, and we would just do this manually. The reason this is not a great solution is because if you really wanted to do this correctly, you would have to turn off bilinear filtering in the hardware and actually take the bilinear samples yourself, because bilinear filtering itself wants the correction of the sRGB done before the bilinear combined. Because remember, if you're trying to do linear math operations, which bilinear, as its name implies, certainly is, you want to do that in light linear space, not in sRGB space, which is an exponential space, where bilinear filtering will not produce the correct results. So, that being said, I'm not sure how to progress on this particular card in a way that makes a lot of sense, because certainly we don't want to we don't want to handicap all the modern cards out there that would have no trouble turning that on. So I think what we have to do here is probably try to figure out some way of detecting whether a card can't do this or not. And if we detect it, then we can do the squaring and square rooting in the shader, but if we don't detect it, then we won't. That seems like the best plan. The problem is that's easier said than done. And the reason that that's easier said than done is just because, well, I don't really know if there's any way to do it other than just trying to create the texture ourselves. Now, maybe that's the best plan, I don't know. And then when we try to create the texture, we will then find that it failed using checkGL error. And then when we find that it failed, we'll try again without that flag and see how we do. That's the only thing I can think of right now. I don't think there's some other way. I don't think there's a capability kind of a query you can do that asks whether or not you can support multi-sample plus sRGB. So I think that's pretty much where we're at right now. I can't really give any more of an estimation than that. So what I assume we're going to have to do here is, if we've got this sort of situation here where we've got supports sRGB frame buffer and default internal texture format, I feel like probably what we're going to want to do here is maybe regress this a little bit and maybe just have something that's like supports sRGB or sRGB support, right? And what we could sort of do here is just say like, all right, if it has sRGB support everywhere, then we turn it on everywhere and we do sRGB in hardware. Whereas if we detect that it doesn't have sRGB support, then we do sRGB nowhere. And we insert into our shader code that will correct for the sRGB that's coming out of the textures. That's the only thing I can think of. There might be something smarter to do, but that's the only thing I can think of right now. So since that's the only actual bug we have at the moment, That's, I think, the first thing to rectify, because we can't really call our rendering done, because there's a bunch of stuff I want to do. Like I want to go clean up how we're, like right now we're still using partly OpenGL fixed function pipeline because I just showed how to add shaders just last week. I'd like to go in and like get rid of the rest of the fixed function pipeline so that we're entirely on shaders and buffers or something like that, just to clean everything up. I'd like to do that, but before we do that, I would definitely like to make sure that we are rendering properly. That's really it. Now, I suppose the other thing I should do too, actually, I guess before I go too far down that road, is I don't remember how we were initializing our OpenGL exactly. So I should probably make sure, just do a check, to make sure that we didn't do something in initialization that would make us, that would cause us not to have these capabilities when we actually should have them. So for example, in our attrib list, right, you can see that we pass a bunch of information here in terms of what we want for our pixels. And then in terms of our OpenGL context, we have a bunch of stuff here like major version arb and minor version arb and stuff like that. So I don't really know which context we would necessarily need. Like it may be that a 3.0 context isn't supposed to be able to have the sRGB frame buffers with multi-sample for all I know. You know, I don't know. So it could be that we just needed to make this go up further. So I don't know if this card supports OpenGL 4.0, but we could try. We could just see what happens. If we did that, I don't know what would happen. But we could take and set a breakpoint in there during initialization and see whether we get higher context if we ask for it. And then if we do ask for the higher context, I could try again to see if maybe in a higher context setting we would get that better texture format handling. I don't know. Like I said, this is totally just speculative on my part. So I'm going to go in here. You can see us getting the extensions here and then our initialization. So in this right here where we do context attrib arb, I'll just step in and see, did we get one? We did not. So it would fall down to a backup context in the case where we ask for 4.0. So 3.0 is definitely the baseline. I don't know if I can ask for 3.1. Let's find out if I can. So 3.1 I can ask for. Again, not sure that would do me any good at all, especially since we have a compatibility contest specified. So I'm assuming it would not. My assumption is that it would not prevent us from doing something with the compatibility bit set. But you know, I don't really know. Again, drivers are very fussy and finicky, and they don't conform to spec most of the time. So I just want to be doubly sure that there isn't something going on there that's preventing us from getting that to work. So if I now come in here and I turn this back on, I'm expecting it to still not work. I'm expecting it to give me an assertion there. Just gotta clean that up. It's like this now. Yeah. And so we still are unable to call that. We are still unable to call GL text 2D multisample. So I'm assuming that it just can't handle that. For whatever reason, this card can't do that. So I'm going to go back to Win32 Handmade and turn that off because I don't think we really need that for any particular reason. So 3.0 context is fine. So in here, basically what I need to do now is have a way of, instead of this being a default internal texture format, I need to have a way of specifying this as not being sRGB and figuring that out. So what we need to do, I think, is go in here and have a test where we basically call this function and see whether we can call it at all. Basically create like a canary in the minefield, so to speak, where we can try to do this call and see what happens, right? So I'm guessing that we do something down here where we would say, all right, you know, GL text image 2D multisample, GL texture, yeah, there it was, 2D multisample. We would specify that max multisample count, which I could just get once. In fact, that could be done, instead of being done here, we could actually pull this out and put it in the OpenGL structure itself, right? So up in here where we've got, I guess it could be GL uint. call it that. So what I can do now is say, all right, I've got that max multi-sample count. I'm going to go ahead and get that from OpenGL. I'm going to clamp it as well to 16 because I don't want to ever be higher than that. That would just be excessive at that point for our purposes. So when we take a look at the multi-sample, we can then use it to say, let's go ahead and try to create one of those. I need to bind a texture here, and I need to bind a, I need to bind a texture and try it, and then undo it. I don't remember if we need to bind it to that slot or not. I think we do. Yeah, we do. So I'm just going to bind a texture to that slot, a dummy that doesn't really exist and doesn't do anything. I'm going to try here to just make one, right? And I'm going to pretend that it looks like the screen, right? So it looks like a dummy kind of screen that we might expect to use. And then we could say, all right, if we can get one of these with sRGB, then we will use it. Otherwise, we won't, right? So once we've set that default internal text form and we look at this, we'll specify the texture. We also want to delete that texture after we're done. So I guess I don't know how to tell it that we don't need that texture anymore, which is interesting. I guess I could GL text image multi-sample with 0, but I need to tell it that it can release the state backed by that. I could do that with delete texture by doing a gen textures and then delete textures. Let me double check to make sure that that's the right way to actually get rid of that. Because I don't want that texture sitting around because it's just taking up graphics card memory at that point. So let me just take a look and see what that does specifically. Oops. So I think we can just call that. So I think we can just call GL delete textures test texture equals 1. And for good measure, I suppose we could actually just have it do it. GL gen textures 1 test texture. And so here, I'm just going to go ahead and create this test texture, see if GL text image 2D multisample works, and then delete it if it doesn't. So what I'm going to do here is just say GL get error to clear the error, and then GL get error to get the error back. So I'll say if GL get error equals GL no error. In this case, actually, what I really want is not equal to. And what I'll do here is just say, OK, in the case where it doesn't work, we'll just regress from what I said, right? We'll go back to just doing RGBA8, right? So what I can do here is I can clean this up a little bit more, too. What I could do here is just say, like, OK, if we're going to do this, we might as well get this guy first, right? And then only if we actually were going to set this to true, let's just only do the test in there. That way I can do it a little bit more snazzily, right? If we were going to do something that would have the frame buffer support and the texture support already, and we think that's going to work, then we would go, OK, let's try the test texture now, do that, and if it equals no error, then we'll go ahead and do it, and we'll enable it here like so. Right? And so then the only change we have to make there is the texture format we were going to use, we have to supply that in here. Right, so now we come through and we say, all right, if we have a chance at supporting sRGB, let's go ahead and try to create a texture here and see. If the texture is created properly, then we'll assume that we can do it. If it's not, then we'll assume that we can't do it. and off we would go, right? I think that's about it. I think that's really all we need there, right? So I'm going to go ahead and test that out and see if that actually works. We don't know if it will or not. We need to go ahead and put that, there we go, GL max sample count. It does seem like 32F. I'm not sure why I put 32F in there. That's probably not useful. We don't really need float. Should probably be 32. Floating point obviously only has 24 bits of precision, whereas an integer has 32 bits of precision, and we don't need a wide range, so we're a very small view distance of what we can see on the screen. So I feel like we just probably want a 32-bit integer there, but that's I don't know why that was like that. That's just how that is. Just how that was, and it should be changed. So okay, we just got to change these to the max multi-sample count variable that we now store permanently. When we do get texture, what is the problem here? GLint. Okay, sorry, it's not an unsigned int, it's a signed integer, apparently. There we go. And I guess what I'm not sure about is supports sRGB frame buffer. I don't actually know who's using that right now. Does anyone know? Support, oops. So I want to do a search. Supports sRGB frame buffer. So that's in Win32. So that's really just used by this. So that's not really a Boolean, right? So really the only thing that, not really a Boolean that we use in the OpenGL layer. So that really all we're talking about here in terms of stuff we care about. In fact, I don't know, that's interesting. I don't know who even sets this or why. I guess it just gets set in the info, would be my guess. Anyway, it's not a very good indicator of it. So really what I want to do is like shader shader sim sRGB. We'll set that to false. And in here what I'll do is say, hey, the shader has to simulate sRGB in the case where we don't support it. I guess I would do that like this. Right? So then we would get down here to our shader code. And in our shader code, we need a way of specifying whether or not it needs to do the sRGB in the shader, right? So what we want to do here is basically introduce probably like an ifdef or something like this. So we've got our header code here, right? And here's the header code. What we want to do is probably do something like, well, okay, here's the header code, which normally doesn't have very much in it. What we want to do is add, do kind of an if that will determine which kind, which we're going to do here in terms of header code, vertex code. What I could do too is maybe when we do OpenGL create program, maybe I have header code and I have defines or something like that, like this. So what I can do is when we actually do that OpenGL create program, that defines will go in here as well. So everybody gets these like pound defines. That's another thing in addition to the header code that goes in there. And that way what we can do is we can have like all of our code pretty much intact. And then we can have our defines. And those would just be nothing. But if the shader has to sim sRGB, then we can set the defines equal to something else, right? And so maybe we set the defines to simulate sRGB or something like that, or shader sim sRGB, right? We can pound define that to be 1. And that way, all of our code in here is free to use a pound define for that shader sim sRGB. Does that make sense? So we're basically just predicating our shaders based on whether or not we got sRGB support or not. I don't know why I put a C in there. There we go. So now when I run this, in theory, we should, wait, oh. What, okay. So I guess the version number has to be with the defines, apparently. And I guess I could use the same syntax we were using before. There we go. All right. And so we can then slip our little pound define in there, and the rest of our code can stay the way that it was, which is good. So I think, hopefully that's good now. And so now what we... OK, that's pretty cool. It's already doing that detection, I guess, and turning off the frame buffer right. So that's pretty nice. All right, so what we need to do now is actually think through the way that we're doing our sRGB and actually have something sensible in here that will work as we go. So if we take a look at what's happening, we're going to have to do a couple different things. But first of all, we know that when we do this test here, we're going to come through and we're going to have a problem where we will either enable or disable frame buffer sRGB. If we enable or disable frame buffer sRGB, what that means is that the final blit where we take and we go from the multi-sample buffer down to the actual buffer that's going to be on the screen, that will be doing an sRGB conversion or not, right? So just to make this a little bit clearer here. So we basically have texture, buffer, and screen, right? And so we have a couple different places. So here's like 2 sRGB, and this is a from sRGB. This is a to sRGB. This is a from. So every one of these arrows has an sRGB conversion on both sides. So the texture, right, is encoded in sRGB. If we have sRGB support for our textures, then the sRGB conversion here can happen, right? So we would not have to correct for that. What we would have to correct for is this sRGB would not occur, right? We would not be able to have sRGB happen when it actually goes to write to the backing texture buffer, right? This is our multi-sample buffer. So one way we can fail is we can't do it here, right? Another way we can fail, similarly, is we aren't able to do it here. And these two, thankfully, happen symmetrically, as far as I can tell, right? So if this texture cannot be set to sRGB format, then both of these will fail, and this is effectively not doing a to or a from, right? Then this one could fail separately, right? This is a separate type of failure, and that's the failure when we're going to go do the resolve, right? So what I would say is we probably need all of these to be atomic. The reason we need them to be atomic is because when we do the resolve, we don't have a shader involved there. Right now, we're not loading anything into the graphics card, and we shouldn't expect to be able to necessarily because it depends on the hardware, that could take the resolve and do something smart with it, right? So what we pretty much have to do is say that there's 2 sRGB flags. There's basically texture read and frame buffer write. Oops. Okay. So basically what we're looking at here is we need to support either of these two things failing. And when this one fails, what that means is something in these two failed, right? It could be either one of them is not supported. We don't care which one. If it's not supported, then we have to simulate it in the back of the shader, right here, right? And so either we have to simulate it on one side or both sides, or one side or the other or both, right? So we're really going to end up with, I think, two different things, which is like sim texture load sRGB and shader sim text write sRGB. And so we assume that we'll have to do either of those two, right? But that we don't know whether we'll have to do both or one or the other. We know on this card we'll have to do the right one. On other cards we might have to do both. On some cards, modern cards, presumably we'd have to do neither, right? So what we want to do here is say, okay, we'll assume we have to do both of them. If the frame buffer supports sRGB and, right, and we have all these sorts of things, then we're going to try this stuff. But honestly, this one is separate. So really what we want to know is a little bit different than that. We want to say if the GLX texture sRGB is there, then we'll assume that the text load is false. Because if we know that GLX texture sRGB is there, then that means we know we'll be able to turn on our texture format. Our texture format for reading textures will be correct, right? And that means we will need a second one here. Instead of just one default internal texture format, we need default sprite texture format and a default frame buffer texture format, right? We need both of these. So what we want to do here is say, okay, our default sprite texture format is going to be set separately because we know that that's sort of controlled differently. And we'll, again, assume in both cases that we will default that we will set it to the correct value by trying to do some checks here. Okay. So we have a default sprite texture format and default frame texture format. The sprite texture format is just if we think we have it, we will use it, and then we will not try to simulate the load. On the other hand, if it looks like we might get the frame buffer, we'll test it and see. And if we can, then we'll do default frame buffer format, and we'll set that flag to let us know we don't have to do that. Shader sim text write. Okay. So now we have to fix up the places that use that. In the code. So here we are when we're allocating texture. This is going to be a default sprite. Everything's going to be a default sprite except that one place that allocates, yeah, this guy, basically. There we go. And so now we just have to, in here, actually handle these. So what we need to do now is have these sort of predicated based on what we found. We may want to make it so that we can sort of create this string dynamically. So what we might do is, since we're in a place where we could concatenate strings together, we could just make something that sort of prints these out into each other. Let's take a look at that here. So here's our format string call. I'm going to go ahead and use that to basically build a dynamic string here. So I'm just going to make this be some giant string that we can stick stuff into. That may be excessive. And so what I want to do here is just say, like, OK, let's format a string. Let's pass it this guy. And then I'm just going to go ahead and pass it some strings here, right? First of all, I guess we have the version one. And I guess that actually, now that I think about it, that can just be baked in there, because we know that's always going to be there. It's the other two that we're not sure if they're there. So then we have one for our text reads. There we go. And we have another for our text writes. I think that was what we called it, right? Shader sim text read and write. It's load. All right. So now we've got one where we can actually build the strings together. So there's the two strings that might appear, and then we'll pass them here. So what I can do here is just say, all right, if shader sim text write sRGB is true, then we'll add that string. Otherwise, not. Same thing with text read. So now, depending on whether or not we want shader sim text write or shader sim text read, we'll put those defines in or not. Right. The other thing I guess I could do, which maybe is a better way to do it, is just have this be maybe just something which prints it out every time, but adds the right value to it. So I could just do a %d there, for example. Maybe that's a clearer way. Right, so then I would just say, okay, print out the shader sim text write and the shader sim text read. Put those two out and just put a 0 or 1 there, depending on which ones are on or off, right? And so then we don't need any ifs at all. We're just going to produce that string concatenated. Then we've got the header code, which we don't really have to take advantage of yet, vertex code, and fragment code, right? So now what we need to do is actually use these, and what I can do is in here I can do an if shader sim text write and a shader sim text read to just correct these. So basically you can see what's going on here in the shader, right? I'm basically adding 2 stages. Here is the place where we sample the texture. Here is the place where the texture gets output, right? And so when we go to write this back to the frame buffer, or when we go to read this texture in those 2 places, I could simulate the sRGB transform myself, right? So what I need to do here is essentially effectively the same thing as we're doing in our software renderer, right? It's the exact same thing. So if you take a look inside the code for Handmade Hero already, and we look at the render code, you can see, draw a rectangle quickly here. Here's our code for this. And let's see. Here's our unpack by linear, right? Let's see. So it looks like this is the conversion here. So you can see, let's see. We should be doing, and of course it's always very hard to read the code when we've optimized it all out like this. I was going to point out where this happens, but let's see. So this right here is actually doing, so this is taking the red, blue, and it's actually lining those up. You can see it masking out the various parts. So this is actually separating out the parts of the texture. And then here, doing the bilinear blend. Here's the bilinear blend of the texture. So it looks like we don't really do this properly. The squaring of the, or maybe we did, and maybe we did it back a little bit further, because this is actually the destination now that I look at it. So this is loading the destination and doing the squaring of the destination. But I don't see where we're squaring the source. And it might just be because we cleverly put in a way to do that in here. I'm not sure. Because I don't see it. I don't see it obviously in here. But maybe we just I'm not looking in the right place. But either or, this is the exact thing we're trying to simulate here on the destination side. You can see it squaring the values on the incoming, and then on the way out, again, we kind of have to do the reverse process. And you can see right here that happening as well, right? We've got the mmr squared ps. So what we need to do is that same process. The r, the g, and the b need to get flipped back up, basically. So when we go to write out, right, and when we read in, we have to do the text sample RGB. We have to be able to do a square here. So text sample RGB has to equal, it basically times itself, right? It just has to get squared. And like I said, in shaders, unlike the way we wrote it, in shaders, when you do a multiplication, it defaults, if it's a vector, to just doing component-wise. So it's the Hadamard product, which is what we would want to square, right? And then similarly, on the result, we need to do basically a square root. I don't know if you can write this way, but that's what we need to do, right? So I'm not sure. Oops. We'll have to check the shader reference card to see whether that, how allowed that actually is in terms of how do you do the square root part of things. I know we had one up before. Okay, so there's our square root and the inverse square root. I don't know whether square root is more performance intensive. If inverse square root is an approximate square root, sometimes that is the case. So I don't know if we can tell it. We may have to use inverse square root and then invert it. I'm not sure. Hopefully we don't have to. So in theory that will just work, and we'll be able to get that to just do what it needs to do. Vertex shader is okay. Fragment shader. Undeclared identifier result. That is not obviously what we want. Sorry, result color. And this is supposed to be result color. There we go. Try that again. There we go. So now we've sort of got a couple of different things happening here. We'll talk about those. OK. So now I believe our colors for our sprites should be more correct, right? And they do look more correct to me as well, right? When I'm looking at them, that actually looks like the correct colors to me, which is good. So I think we now have everything working properly on that path. So when we, and properly I mean for the case where the shaders, where multi-sample doesn't support it and we have to simulate the sRGB in the shader, right? Now, we don't have another card here that does it properly, so we can't test to see whether our path actually works, because part of our path is supposed to turn this off when we get in the circumstance where the card can do it. So we really need to test it on another piece of hardware eventually, which we'll try to do. But at least we have it working, I think, correctly in our particular case here. Now, we do have another problem, however, and that gets to the next set of things that I want to do. And that is that the rest of the pipeline, however, doesn't go through this path, right? The rest of our pipeline is still fixed function and still doing things the old way. And so, for example, our cubes are still the wrong color, because our cubes are still specifying colors in sRGB space, but that path is unaware of the fact that the frame buffer does not support sRGB conversion, right? So it's still using the wrong colors, which means our cubes are darker than they should be. Everything else is correct, but that is not. Okay, so we're definitely getting closer, though. Like, our little hero guy, I think, is now more the correct color that he's supposed to be. He looks right to me now anyway, whereas before he definitely didn't. And so I think we're in better shape for that, but we still have to deal with the fact that the other code is, the rectangle code and the cube code is still kind of on the antiquated path. So that's, I think, where we need to sort of move towards. We also have a few other items that we want to take a look at eventually, which is basically we want to segregate our code out in terms of stuff that has transparency in it. You can see right now that, for example, our shadows in like these cases which are doing alpha, remember, we no longer have really any alpha per se. We only have multisample, which means that we end up in a circumstance where our because we have the only 8 steps of alpha due to the fact that multisample, we only have 8 times multisampling on, you can see a lot of banding in anything that's transparent. You can see it in the fade out of these guys, you can see it in the shadows, and so there's probably some things we could do there that would increase our fidelity by not always relying entirely on multisample for alpha, and maybe doing something where we segregate, for example, our sprites that have transparency, like the shadows do, segregating them into a separate buffer so that they can get rendered after the fact without z-checking, for example, would be one way that we can make that work. So we may be able to do some things that will drastically improve the quality of those sorts of drawing operations, but we, like I said, there's costs associated with everything, and so you'll have to see as we sort of go through it what the trade-offs are. But at least for things like shadows, which tend to occur in isolation, and where mistakes are not as visible on them, there's some pretty easy ways we can get free real alpha in there, and so we probably will want to. Okay. So that's it for the sRGB part for now. Like I said, we kind of need to play around with that on some better hardware that can actually play around with this and see what's going on. I think all this stuff should now be more correct and something we can use going forwards. What we need to do now is just take a look and see about modernizing the rest of the parts of the pipeline that we were sort of leaving in the old school format. I want to take a look at bind frame buffer here for a second, just to see how that's working. All right. Okay, so what we need to do now is basically just go through and start to clean out the parts of this that are sort of working differently. Now, one of the things that you'll notice if you take a look at how this code is structured right now, so you can see that we've got our render entry bitmap code here, and you can see that basically what it's doing is it's kind of taking these vertices, and it's doing a very predictable sort of blowing out, if you will. It's taking the vertices and it's doing a specific sort of amplification of the information that's coming in, which are these like axes and stuff. And then it's doing this sort of like creation of these with the Z bias and whatever, right? And then if you come down here, you can see the render entry cube, and it does exactly the same stuff, right? It's taking in some inputs and it's doing this amplification, right? And then you get down here to render entry rectangle, and that's effectively the same thing too, right? It's calling the OpenGL rectangle call, but otherwise it's pretty much doing exactly the same thing. And so what I want to look at today is let's, in preparation for sort of cleaning all this out and making this more concise and useful, let's talk about maybe what if we were to just change the format that we submit these things in, and we just always submitted them as, quads or something, right? Like we always submitted them as, or as triangles. You know what I'm saying? Something where we would just say, let's clean up, let's not have multiple different typed things that can come in terms of drawing. Let's just have everything just draw textured triangles, since that's what we know we end up doing at the low end, right? And furthermore, since we know that we're actually always textured quadrilaterals, not textured triangles, maybe we can figure out a way to make that work as well, right? So let's try this. Let's just try moving it that way. And so what I want to do here is I basically want to get rid of these other paths, and I want to bake these paths into the render group side of things that's on the app side, and have the OpenGL output side, all it deals with is just textured quads. That's it, right? That's what I would like to do. And so, yeah, if we could go ahead and do that, I think we might be in some interesting shape here, because then that sort of simplifies our renderer down quite a bit. We can start to do some more useful stuff with it. OK, so if I were to do that, let's go over here to render group. And what I'm going to do is I'm going to maybe say, let's say we had a render group entry that was like render group entry type, textured. Right? So basically, I'm going to introduce a new type here, and I'm going to use that type to sort of maybe slowly move everything over to that type, and then I'll just delete the rest of the types that aren't extremely specific. Like, for example, this one we'll probably need to leave in there, the render group entry type render entry blend target. Right? There's things that do like compositing operations like that. And that would probably have to remain, At least I would think so. OK, so, let's keep going with this. So if I have a render entry textured quads, what I want to do here is say that I have such a thing as a textured quad. And this textured quad is going to be sort of just the minimal information you would need to make that happen, right? So the textured quad, in this case, is going to have maybe a textured vertex concept. And so what we would have here is I'm going to pack the color down. So I would say at every vertex, we would have a color value. I'm also going to say that we probably, I don't know if we need texture coordinates or not, because really they're just going to be 0 to 1 pretty much all the time. So I don't know that those are super necessary, actually. They could just be inferred, would be my thought. So it's a little bit hard to say. But for now, I guess we could say we'll pass down the texture coordinates. Just why not? So it's also going to have texture coordinates. So this will be like a UV coordinate. And then it's going to have a position coordinate as well, right? And if you look at the way these are structured, it's a little bit unfortunate because we end up having, with our textured vertex here, we have 4 floats, right, which is 4 32-bit values. So we have 1 pack of 4. Then we have 2 plus a third. That's the same space as a float. So it's kind of like there's this is a little bit of unalignment here. It would be nice if we just had one more thing. But we don't really have one more thing for the vertex, right? Now, that may be OK, because, again, I think graphics cards tend to be pretty good about being able to deal with the unaligned, packed sort of formats of stuff. So it's probably fine, but I'm just pointing out the fact that, I'm always like, try to get things lined up into good chunks, but yeah, neither here nor there. So we basically have 4 vertices per quad, right? And so 4 of these, at least, that's one thing we could say will come out nicely. So in this case, where we've got 7 of these, we've got 4 plus 2 plus 1. So we've got 7 of these guys, but we're going to do them 4 times. That ends up with 28. It's not quite as bad, I guess. Maybe not. But, oh wait, no, that's actually good. That's actually pretty good. Because if the textured quad itself is that size, I suppose we could, well, yeah, I don't know. I'm kind of babbling at this point. Let's forget all that. All right, so here's the next part that we have to think about is for every textured quad, we need to specify a bitmap, right? So there's some bitmap that has to be specified in here. And that bitmap has to tell us effectively what texture went on this quadrilateral, right? That's what we need to know. And so, you can see that if we were doing this in software, that's a pretty reasonable format for it. But as you know, vertices and textures are sort of handled completely differently, unfortunately, excuse me, on the graphics card, right? So we do have this sort of nasty problem where vertices are things that we want to submit to the graphics card, but textures are things that we have to handle outside in our loop. Now, it's worth noting that this is only because graphics cards haven't been completely modernized yet. It's actually not true at a fundamental level. So for example, let's say you're on an NVIDIA card, a modern NVIDIA card, right? Well, on a modern NVIDIA card, it's actually the case that you can have a texture pointer. You can actually have that inside the shader. So you can actually have something where you've got, vertices and a texture pointer actually on the card. And the card, as it's doing rasterization, can actually go use that texture pointer and change that texture pointer per primitive if it wants to, right? NVIDIA cards are very general purpose at this point. And they allow you access to a lot of those features, which is pretty awesome. AMD, it's pretty much true as well, although the access to it varies more due to just driver things and stuff like this. But the real problem, the thing that pretty much always holds it back, is not those two. It's the Intel chips. The Intel chips still have a lot of sort of antiquated notions about what is state that has to get managed on the outside and what's the state that has to get managed on the inside. And so, even though on a modern GPU, you could think of a lot of things like the pointer to the texture as actually being something that's actually dynamic in the shader, that is not true because of the limitations of some of the of the integrated graphics parts from Intel make it so that you can't just do it that way. But someday, we will be out of that world, I hope. That day just isn't today. So what I would encourage us to look at here anyway is just the concept that, well, what we might want to do instead is say something like, bitmap array and vertex array, where we know that we would just be taking these vertices, say 4 at a time to create the quads, but our bitmap pointers would actually be, sort of stored in a separate referencing array. And the reason that I say that is just because, as we move forward with trying to make our hardware path maybe a little bit better, you can imagine us wanting the vertices to be all in one nice packed area that can just get sent to the graphics card, as opposed to, as opposed to having to segregate them first out of the bitmap array, out of a packed array that has both bitmaps and vertices in it, is all. So I'm thinking that we probably want something more like this. So rather than having individual texture quads, which is the more logical way to think about it, we may want to have them as 2 separate arrays. So kind of like we do in SimDland, where you have a structure of arrays rather than an array of structures. We're very much going that way. I think with this, we will want to go that way, where we can sort of start to segregate stuff out, things in bulk that can be handed to the graphics card as a chunk, like in this case where we have this vertex array. I think that's more what we want to do, right? Now things get even more complicated than that potentially, because we may also, in this case, want to do something where we have that memory provided or aligned or specific to how the graphics card is operating, we may want that textured vertex array to be a chunk of memory that the graphics card gives us rather than a chunk of memory we hand to the graphics card, right? And the reason for that is, again, we kind of went over this a long time ago in Handmade Hero, but I'll just specify it again. The reason for that is if you think about how these things are working on a PC where the memory is disaggregated. So we have GPU memory and CPU memory. Remember that these two things are not the same. They are in different places on the motherboard, right? And furthermore, the CPU also has cache, right? Which is not the same. So there's a memory hierarchy here, and this is the slowest of them all from the CPU's perspective, because in between the two is the PCI bus, and anything that we want to do has to go through the PCI bus. Now, maybe on some super fancy schmancy situation, it can go right from the cache to the PCI bus. In other situations, it might have to write through the main memory to the PCI bus. Who knows, right? None of that is really important to us. At this point, it's just important to recognize the fact that there is a big old special bus in between the CPU and the graphics card memory, no matter what we do. And so you have to account for this, right? What that means is typically we may, and because of the way that these two are operating in parallel, right? These are two different chips operating in completely different clocks at completely different times. What we often need to do is build up in CPU memory a buffer of stuff. And then later, the GPU will kind of come across the PCI bus, get this stuff, and it will get transferred back, right? So it will sort of fetch that memory over to itself where it can actually use it for drawing. What that means is this may have to be placed in special memory, right? A special region of CPU memory. And that region has to be a region that's set up to be mapped to the GPU, right? The GPU, depending on the architecture, cannot necessarily just grab any part of CPU memory. It may have to grab a part that's specifically set up for its transfer. Why is this? Well, you have to remember that virtual memory exists on the PC, right? Everything that we do in our CPU on the PC at our level, which is app level, it's above the kernel, right? Everything that we do doesn't deal with actual physical addresses. The addresses that we deal with are virtual addresses, which are translated by the CPU's virtual address table into actual physical addresses of hardware in the machine. So every time we give an address and say, hey, here's a place in memory I want you to read or write from, it's actually going through a translation table to find out what the actual address is of actual physical memory that it can send out to the memory bus to actually get that, or hit the cache to get it out of the cache if it's hot, right? So at some point, right, there is a physical address, and that physical address is what's actually used when you actually go out the bus to memory to get it. But in terms of what we're talking about inside the CPU at our app level, all of the registers are actually containing virtual addresses. Now, why this is important and why I'm bringing it up now is because the GPU, when it fetches things across the PCI bus, it is not made aware of the CPU's virtual addressing table. Why? Because if it was, it would have to have this whole separate scheme of syncing all of the virtual address tables across to the GPU. Right? Which is a complete waste of time most of the time, because most of the memory that the CPU is using in virtual addressing isn't memory the GPU ever needs to access. So you'd be spending a ton of time syncing virtual address tables across to the GPU, and you'd have to synchronize that access so you knew that no one was ever accessing the wrong thing because someone didn't get an update or whatever, right? It'd be this huge mess. So what happens is the GPU needs to know physical addresses usually, or at least not necessarily physical addresses, but at least like consistent addresses, right? When you give the GPU something to do that involves main memory, it has to have a reliable way of accessing that memory and not having to worry about the CPU changing what that memory means out from under it, or changing where that memory is located. So when we talk to the GPU, we can't just send down a virtual address from our process space, because we don't even know if that memory is resident, right? For all we know, that memory could have gotten swapped out to disk or something. Right? The operating system could do whatever it wants. We have no idea. So, as a result, in certain circumstances, depending on the architecture, depending on the driver, blah, 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 what we may want to do is use memory for writing our vertices that is specifically set up to facilitate GPU transfers without a copy. And what that means is it would have to be put in memory that is locked. It has to be put in memory which is locked to a known physical address, and which the CPU and operating system will not move until the GPU can use it, right? And so there's facilities for doing this, and we'll take a look at those potentially later. It's not always a good idea to do it. Depends on the circumstances, like I said. But in order to allow our renderer to take advantage of that in the future if it needs to, we may want to be aware of the fact that the platform layer, the operating system layer, may be the thing that gives us the memory specifically for doing things that do GPU transfers. This is less true for textures, and the reason that it's less true for textures is because textures are swizzled. So depending on whether there's hardware swizzling or not, and all these other things, whether or not you actually care about your textures being put into memory that's locked is a separate issue, and it's less likely to be true. It's sometimes true. It depends. This is the nasty world of multi-GPU programming. But in terms of vertices, vertices are not swizzled when they go down the pipe. Vertices go down just as they are. And so it oftentimes can be useful for you to put vertices into a buffer that is in a place where the graphics card can access it, and it does not have to be first copied into a locked down memory range before that happens. So again, a lot of like hand waving there, because we really just don't know on the PC usually what of a suite of things might be happening under the hood, because it depends on the card, depends on the driver, depends on a lot of things. So we don't know, but what we do know is that it's possible. And when something is possible and we know we might want to take advantage of it, that means that we need to architect our the way that we have our things set up at the higher levels of the code in order to make sure we don't preclude the possibility that it happens. And so that's why I say this is something we want to think about, saying, hey, the vertex array that we're dealing with here, we probably want to have it so that that vertex array can be stored in GPU locked memory, in CPU memory that's been locked for GPU access, in case that turns out to be an important transfer criteria. Will we be hitting the case where we actually care about this? Probably not. But again, just trying to show some of the concerns here that you might have. We probably will not be pushing enough vertices for that to matter, but if you were talking about a heavy vertex throughput situation, it's something to be aware of. All right, so when we do render entry texture quads, what I'm thinking of here is like, okay, we've got a loaded bitmap, we've got a bitmap array, we've got a textured vertex, and that's going to point to this vertex array here. We may want this to actually be more of an index. So we may want this to be like vertex array offset. And then that textured vertex array would be something that was more like stored on the render group or in the render commands. So like in the game render commands, for example, there they are. So in the game render commands, when we've got this situation here, and we've got like the push buffer and that sort of stuff, I'm thinking of something more like this. So we have a vertex array here. That's what we would be writing into, and that vertex array is filled with these textured vertices, right? Like so. And so I've got this textured vertex array, and I can write into it, and now it would be something that is provided to us from the system, and we're just sort of writing into it. And so then when we have something come down the pipe like this, where we say, here's the textured quads that we're trying to write, here's the offset into that vertex array that I expect you to use to start with. Now we know we can just have one big bulk buffer of vertices, and then we're just sort of talking about, hey, I need you to use these vertices out of that vertex array, right? And again, that's just a step towards making things a little bit more efficient than they otherwise would be. And so, you know, so then all we really need here is to round it out would be how many of them there are. And so we just have like an array of bitmaps pointers which say which textures to use, and then we've got how many quads we're going to draw and the offset into the global sort of, it's not really global, but it's, you know, it's global to this render pass array of vertices that we're just writing into with all of the vertices that we ever need. So then, when we're done with a frame, we can just turn around and say, hey, graphics card, take this whole vertex array, just the whole thing. It's all in there, right? And then, you know, we can piece it out and say, draw these with this texture, these with this texture, these with this texture, and so on, right? And that's really all we're talking about. So that's sort of, I guess, what I'm getting at for how we could start to sort of transition these things over. All right. So let's say we're on the OpenGL side. How would we implement something like this? Just as a first pass, just to get it working. So let's say we're here. We see one of these textured quads doodads, right? Well, we know how to draw one of these guys, right? So I'm just going to start with that code. And what I want to do here is just encourage you to kind of look at how much work. So this is to draw one sprite. And look at how much work is involved here. We're actually setting up like what program to use. We're setting up these matrices, right? We're setting up like all the stuff that needs to happen here, right? And a lot of this stuff is just busy work. It doesn't need to be done every time. Certainly, we don't need to change the program every time. If we're using this program for all the quads, you know, that's something we can do once, and then every quad can use that, you know, going forwards, right? So we can set the program once, and then we can, you know, for every quad, it's just sending down a new quad with the same program. So already we can save that, right? The same thing is true of our transform matrix here, right? Probably we could just save this and the begin. All of that stuff doesn't have to happen per triangle either, right? So all that stuff comes out. Let's go ahead and make our for loop here for each triangle. And so then inside our for I loop, what we're doing really here is saying, hey, we've got a quad index, and we're going to go through to, our quad count here. This is, I got to change this to render entry textured quads. Yeah, and off we go. So let's take a look here. We would just say the entry quad count, like so. And we now know we have basically a few pointers. We've got our vertex pointer, which, hold on a second, where did we go here? So we've got this vertex array inside our game commands. And we know the offset of that because we know inside the entry we have the vertex array offset. Where'd that guy go? Right here. Right, so we know the vertex array offset that we're talking about. So we know where we start in the vertex array. So this is our textured vertex. So that's the vertex we're looking at the base. We then have the count, which we know is how many of the quads we're going to do. And we have a pointer to the bitmap that we can sort of advance as well. So we can say, like, here's our bitmap. And that's just going to be equal to this entry's bitmap array as we start with, right? Like so. All right, so we know that stuff, right? That's all pretty basic. So now as we go here, what are we looking at? Well, we've got a loaded bitmap. I suppose I should probably do it this way. Something like this, or maybe that. And so I can say, okay, the bitmap is the bitmap at this point, and we'll advance it 1. Because we know for every quad we draw, we need to load a new bitmap out. And then the textured vertex, we know is the vert at, right? But we know that we're going to have 4 of these, right? So we know that we're going to have like vert 0, vert 1, vert 2, and vert 3, like so. So we can just grab those out as well. And now we have everything we need to draw with, right? So now we don't have any of this stuff anymore, right? None of these things are going to be here. We do have to bind our texture, obviously. I don't know that we need to bother with this if. I don't think we do, because our texture coordinates are packed in there. So we don't have to test this anymore. And so we really just need to do the bind texture. Now, I suppose this is a case where until we use something more advanced in the fixed pipeline, I'm not allowed to bind a texture inside a begin end. So for now, I will have to turn that off and put it on the inside. But eventually, we will want that on, to be more efficient as well, probably. So I need to, again, bind the texture here that's coming in from the bitmap. So we'll do that. So we'll make that like that. And then I've got, these are all for creating the UV coordinates, which we're assuming we will do on the other side, because they're already packed into the vertex, right? So what we need is, in terms of our values coming in, we do have a color, and we need to specify our color to OpenGL. That color is a packed 32-bit value. So we want to be able to specify that color as like a GL color for UB, basically. And you can see here the one that we actually want, which is, whoops, that's 3, which is this one, GL color for UB. Now we have to unpack it. So again, this is going to get more streamlined when we switch away from the fixed function pipeline, because that unpacking can happen automatically in the vertex shader, actually. So this is actually going to be a lot less efficient right now than it will be when we're actually reading them directly. But I want to do it one step at a time, both for ease of debugging and so that you can kind of see the steps as we go through them. All right, so what we want to do here is we want to do a GL, and we probably want to do this as a separate, as like a macro, basically, which is like color UB macro or something like this, where we can just specify in here this color, and it will unpack it, right? So what we want is something like this, where we specify, a color value. And then that color value translates into a GL color for UB, where we're actually going to do this sort of thing. So we're going to take that, that packed version, and this wants RGBA. So the R value, in our case, as far as the packed colors are concerned, we have to pick some kind of a format. So I'm just going to specify that this is RGBA packed. So it read ABGR in a register, for example. So that means that the bottom is the red, 1 up is the green, and then we get to the blue, and finally the alpha is packed at the top, right? So that's what I want to specify there as my color, so we're going to go ahead and specify that as the color. And so we know that we would specify a color per vertex. right? We also specify UV, and so we know how to specify that as well, which is like this. So our GL text chord 2F can be a 2FV in this case because it's just the vertex UV. And then same with the vertex 4FV, we know the position we actually have as well. Right? So we know that's what we're putting out. Right? So now we just need to do this in a way that's actually going to draw it as two triangles. Now, what would be nice is if we could just do GL quads, which unfortunately, I think in the fixed function pipeline we could probably still just do. Eventually, we'll have to do a little trickery if we want to get the modern pipeline to do it, because there's no such thing as quads. You have to kind of set up a tri-step with a restart. It's kind of wonky, but it's doable. So what I probably can do is just do it like this. If this card allows me to specify quads, which I don't remember if it does or if it doesn't. So that's going to be anyone's guess, really. Whether that'll work is a really good question. Probably I should try it first somewhere else to see whether it works before we go diving in there. So yeah, that's something I'll go do right now. So these all have to specify the float part of them because it doesn't understand how to take the structure and produce a float from it. So there we go. And so that path isn't getting called right now. We're just calling this old path still. So it's neither here nor there, but one thing at a time. So what I'll do is I'll just test to see whether quads work or not. I can go up here into where we were doing this before and say, if we change this to quads, does that work temporarily? Because we're going to want to draw as quads later so we can specify less things to the graphics card. So here's that lower triangle, and then we just need the upper triangle. The max version is there, so we need the min-max version, which is where... There we go. Yeah, so that's fine. So we can use quads for now, and then we'll show how to kind of do those, because eventually we're going to have to switch away from GL begin and individual text chords sending down and that sort of stuff. When we get to that point, I'll explain kind of what I mean by quads not being supported anymore and you actually do something different. It's a little wonky, but it's basically, it went from being something where you specify how primitives are assembled in a way that makes it reasonable to specify quads to having sort of more flexibility about how primitives are assembled, but as a result, you have to construct the ability to make quads yourself, kind of, if that makes sense. So you'll see that eventually. All right. So here is sort of a way of outputting these textured quads, and you can kind of see how this works. It's very straightforward. The only kind of wonky part about it, and the thing that's a little bit problematic, is just you can see that we sort of have this problem of binding the texture every quad, right? This is actually one reason why, depending on the hardware you're on, why people like to use things like texture atlases, for example, or other things like that. Those are really just workarounds. Like, there's no point to a texture atlas, right? Other than to work around basic limitations, one of which being if texture binding is expensive, so that because you can't put it in line with your other data. Another reason if graphics cards cannot efficiently manage non-power of 2 textures. There's a lot of reasons for it, but they're all just basic workarounds, right? They're just workarounds from the concept that you can't deal properly with having just in line with things a pointer to an arbitrary rectangle that you're trying to blit, which is what you would have wanted for drawing a sprite. So anyway, we've got this situation now where this should draw quads nicely. Of course, we just now have to feed it some actual quads that it can draw. And so what we'll do at first is we'll just start by setting up a circumstance where we can feed our sprites down as these quads and see how that goes, right? And that's what we'll try to do. So we have two problems that we need to address. One is the bitmap specification array, and the other is the vertex specification array. The vertex specification array is the one that I want to come from the platform side. So when the game commands themselves get allocated, render commands, here it is. So when the render commands get specified here, you can see where the push buffer gets put on here. In addition to these, and we do render command struct, that render command struct now needs to have some additional information with it. So you can see here like the push buffer width height stuff going on here. And so then there's the push buffer and the push buffer base data at sort of situation. So what we want to do is also specify this vertex array. So that when we have this render command struct, it needs to specify that. So if we come back here to where the push buffer is created, and you can see that happening here, for now what we can do is just specify the vertex array as well. Now what we might want to do is say max vertex count just for our own checking purposes. There's no other real reason for it. It's just for our checking to make sure we don't go over. So I don't know what our max vertex count is. Let's say our max vertex count is going to be 64K of vertices. Why not? And so when we Win32 allocate this memory, we will go ahead and do max vertex count times size of textured vertex. And then and that's it. So now we have a vertex array. And we need to actually start using that vertex array and putting stuff in it, obviously. Max vertex count. Yeah. And we need to actually write the vertices in there, and we need to figure out how we're going to write our loaded bitmap stuff out. And I don't really know. At this point, to be completely honest with you, I'm not sure how I want to do that. I mean, I kind of feel like it probably should just be part of the push buffer. Maybe. I mean, I think that's almost certainly the right way to do it. So let's do it that way. It's high allergy season here, folks. And I'm a snotty boy. All right, so let's go ahead and take a look at how this will work. Inside the render group, what we're going to want to do is have a way of just kind of like aggregating these over time. So inside the render group, probably what I would do is say, all right, we've got this render group here. The render group is going to have a thing in it called textured vertex what's it called? Render entry textured vertex, textured quads. That guy. I'm just going to have a thing called current quads, right? And what this is going to do is current quads is going to have a thing. It's going to have some calls associated with it. And so what I'm going to have here is like begin quads. And end quads. And what this is essentially going to do is it's going to like push an entry onto the render group that's for the quads as they're getting pushed on. And what I'd like to do is I'd like to kind of have that be part of the push, the push entry structure, if you will. So when we do a push render element, I think I'd like that to kind of be in line with it. And so what I want to have happen here is like when we push a render element on, I would like to make that, well, I guess let me not go too far with that yet. Let me just see, because I kind of got to work with both of these at the same time here till we remove the other kind. So what I want to do here is when we do a push bitmap, instead of calling push render element, what I really want to do is take all this code that I had here, and I want to just do what it was going to do inside the OpenGL code, right? So remember, this is what it used to do, is this stuff, right? So in here, what I'd like to do is something more like this. Is this still happening? That is very interesting. Hold on a second. So in this case, if the sprite was flat, it doesn't, oh, I see. We use the camera axes only if the sprite is not flat. If the sprite is flat, then we just use the regular axes. All right, that's fine. Anyway. So what I want to do here is I want to just do this right in line. So rather than storing up the information necessary to do this, I want to get rid of all this stuff, right? But I want to actually sort of have this do all the sort of the blowing out of the data right in line. Now at this point, assuming we have a bitmap, we never call push bitmap on something that doesn't have a dimension. So I think that's probably fine. Am I right about that? Yeah. So the bitmap has to be filled in. So we can actually do this. One thing we can do is, since this can't be drawn if these aren't both here, I suppose I could just make this whole thing predicated on that, actually, right? And basically say, all right, you know what? If the bitmap isn't valid, then we're just not even going to entertain that at all. So when the bitmap comes in here and we do all this stuff for it, instead of this pushing of the entry here, we're going to do something slightly different. But before we get to that, I'll also say that, you know, like the x-axis, that sort of thing, these are actually going to be there's a bunch of noise outside that sounded like dramatic. I don't know if you heard it. There's like sirens and things. I don't know what's going on. We don't need another pointer for this. All right. So if you take a look at what goes on here, we sort of have the situation where we can collapse a lot of this work that we were doing here. We can just call this min p if we want to. We have the Z bias, it's already there, right? So we've got all this information that we can use, and now we can directly do the computations that we were deferring to later. So we just directly do all of these. Obviously, we don't need any of this stuff. Where's our premol color? There it is. So now what we need to do is we just need to create these vertices. We need to write those out as our verts rather than calling GL to store them in some way, right? So we still compute all of this information, and we need the color value, but we need to be able to pack the color down here. And so I believe we have a packing call. Do we? Somewhere? I just don't know what we called it. Yeah, there's like crazy stuff. I want to know what's going on outside. I'm going to go look. Hold on 1 second. Sorry to interrupt the stream. So I'm not sure what is going on outside, but it's kind of nuts. Like there's like a bunch of police outside, and there's like loud kind of explosion-y noises, but I don't, and there's tons of people like lined up on the streets. I don't know exactly what it is. It might be a protest, or it might be a parade of some kind. I have no idea. That's a very, I literally don't know what's going on. This is the hazard of being on stream in downtown Seattle, I suppose. Let me see if there's an explanation of what's going on here from somewhere news related. Let's see. I don't see anything. I do not see anything. So I guess it must not be anything particularly weird. Maybe it was just something that was supposed to be happening. I do not know. Anybody know? Anybody know? Does anyone on the stream know? Ah, Quartertron looks like he posted something from Como News. Live police fire scanner. What is that? Ah. That's pretty cool. Yeah, does anyone know what it is? I don't know. Well, okay. It's rather disturbing, I will say. It doesn't make me feel super comfortable sitting here streaming with this going on outside, but I guess it's better than being outside. If you see me duck down at some point during the stream, yeah, I may have to end it prematurely. How long? I don't know how long is left in the stream. What time are we going till? 1:15, I guess. Is that right? I don't remember what time I started. 1:30. I started at 1:15, right? So yeah, I guess let's try to survive for 15 minutes more. Yeah. All right. Anyway, so moving on, if I just want to write these out to a vertex stream, right? Then I'm just assuming that I have here a pointer to somewhere in the vertex buffer, which we'll worry about how to get the right one later. But I know that I'm going to eventually have these textured vertices, and I have to write them out, right? So at some point, I've got a textured vertex star vert here. Whatever that textured vertex star vert is, that is going to be where I'm writing, and I'm going to, like, you know, output one vertex, advance it to the next one, output one vertex, advance to the next one, right? So what I need to do is just write to my vertex. I need to write the P, I need to write the UV, and I need to write the color, like so. Now in this case, we need to pack our color down. Like I said, couldn't quite find that. So we'll take a look at how to pack that down in a second. We could just write it in line here if we can't find the existing one. And then I need to sort of like keep these, all of the rest of this stuff exactly as it is, right? So the position of the first vertex and the UVs of the vertices, these are actually going to be all exactly as they appear here, right? So I'm literally just streaming out to this buffer exactly the same stuff that I would have been streaming out to the OpenGL immediate mode old school fixed function pipeline. I'm just putting these into memory. So there's really no, I'm not doing anything differently in terms of the computation or development of the values. All I'm doing is I'm just writing to memory what previously we were handing to OpenGL by a series of fixed function pipeline calls. That's it, right? So I'm literally just making a very simple mechanical change to what's happening to the vertices, and that's it. Okay? So this will write out effectively the 4 vertices of the quad. And like I said, what we want to do here is we want to write these out sequentially so that we're writing to, excuse me, so that we're writing to 4 different vertices, oops, that comprise the quad. Or I should say that constitute the quad. So there's our 4 vertices, and then after we've written them, we would want to advance the vertex pointer by that, by 4. But again, we don't really know exactly how we're doing any of that stuff yet. So we need to sort of have a more coherent system for that in place, and we'll deal with that in a second, right? First, what we need to do is figure out a way to smack this value down, right? Because this is currently a vec4 that's coming in, that's a pre-multiplied vec4. We need that pre-multiplied vec4 to have some more, be compacted down, be a little more concise. So we need some way to pack those colors down. And let's see, like I said, I don't know. I thought we had written one of those, an RGB, one of those. In fact, I know that we have. I just don't know where it went, where it scampered off to. Okay, here we go. So here's pack 4x8. And what you can see here is this is pack 4x8, but it's in the old format, right? And so we want, in addition to pack 4x8 and unpack 4x8, I think we also want them to have both versions of these. So what I probably want to do here is say, hey, let's go ahead and go to the math library. Let's put these packing calls in there because they're pretty generally useful, right? And then what I'd like to do is have both versions of them. So I want unpack 4x8 and pack 4x8, and I want RGB versus RGBA versus BGRA, right? So this would be BGRA unpack and BGRA pack. And then we want the switched version as well, right? So we want both of these. So instead of, in this case, where we've got ARGB in descending order, we want RGBA in descending order there. And the same thing is true here when we're going out to RGBA. So it's just flipping those two around. So this is going to be an RGBA pack, 4x8, right? That's going to pack it down. And that's, yeah, all we really need out of that. So let's see here. Wait a minute. What is x-axis? Oh, x-axis and y-axis are in here. So we're going to call this x-axis 2. This is the two-dimensional sort of version of that. And we can make this code much more efficient now as well. And we got to change these guys. These are BGRA unpacks. OK. All right, so I think we're good now. All we need is a way of actually streaming out the bitmap and texture vertex data, which we don't have. So now we've got the code ready to do all the writes. We just don't have the actual writes themselves. Similarly, you know, we need somehow here we need to do like star bitmap out equals bitmap, right? I mean, we need something like that, and we don't have that either. So in both cases, we need that, and we also need some way of advancing those forwards and that kind of stuff. So what I want to do here in the render group is when we open the render group, I need some way of specifying where those pointers are, basically. And when we do the begin and the end stuff, we need some way of saying, here's where, you know, in the buffer hasn't been taken yet. So I think that probably, since the render commands actually care about that a little more specifically, I think that has to be in here, right? Because if multiple people open a render group at different times of the pipeline, they need to be able to know where they're writing into the sort of that vertex array memory and so on. So we need probably a max vertex count and a vertex count, right? And so we need that to be specified like this so that it can sort of output as it goes, right? OK. So when we're writing to the vertices, that one is probably as simple as actually using the render commands themselves. So that's actually kind of pretty straightforward, I think. What we can do there is just say, all right, we know we've got our render commands. The render commands have the vertex array in them. And we know we're going to write into the vertex array at the location that is currently indicated by its vertex count. And then we need to increment the vertex count by 4 because we're going to use 4 vertices, right? But I think that's all we really have to do. Similarly, when we do that, we should make sure that the amount that we've used is reasonable and has not exceeded the maximum, right? I think that's mostly what we need to do there to make that work. Now, here in the binary operator equals situation here, you can see that I've accidentally kept the part that OpenGL needs, which we don't actually need, so get rid of that. And so that leaves us with only one thing, which is the bitmap out part, right? OK. So now we're definitely getting much closer. And we have thankfully avoided getting shelled by whatever bombardments were happening outside the window, which is also helpful, I suppose. So what we need to do now is figure out how we're going to actually take the render entry for the quads and output it. Now, what we can do just at first is as a pretty basic way of getting this working, is to do the absolutely dumbest thing, which is to push one render entry textured quad for every time we do this, which is exactly the opposite of what we want to accomplish, because the whole point of this is to do multiple of them at once. But we can start by pushing one each time, right? And if we do that, then we should be able to get it working and then add a thing to the render group which aggregates them. So then whenever you call push bitmap, it just sticks it onto an existing one that's in there. And so that's where I'm trying to get with this, right? But if we just do it one at a time now, then it's pretty straightforward. What we need to do is just have some place to put the bitmap out stuff that we're talking about here. When this entry comes back, we know what the entry has to have in it, right? The entry is actually very, very straightforward. It's just these three things, right? So the entry bitmap array, we need that to exist somewhere. We have the quad count. The quad count we know is 1 in this case because we're not aggregating yet. The vertex array offset, we know what that is. It's the command's vertex count. And so all we really need to do here is have that bitmap array be something we can use. Now, when we call push render element, I believe there's the size here, right? And so what I want to do is I want to use in this push render element, I want to actually use something a little bit squinky here, to use the technical term, where instead of calling push render element through the macro, which does the cast for us, I'm going to do something a little bit squinkier, and I'm going to say, hey, let's call the actual function itself. Let's go ahead and put into the what is this called? Render group entry type. There we go. I'm going to go ahead and actually call the function directly so that I can say, give me the size of one of these things plus the size of a bitmap pointer. So now I know I've got some extra size at the end of this thing. And so when I am done getting that back, I know if I want to, I can tell it that the loaded bitmap array in question is actually just going to be right after the entry. So I'm pushing the entry memory, and I'm just saving some extra space at the end of it for that loaded bitmap, right? And so what I'll do here is say, OK, the entry bitmap array is going to be equal to the bitmap that comes in, and I only have to push one of them, right? This needs to get specified. There we go. And so now I think I'm actually pushing those on, right? I believe, anyway. So hopefully that's good. Of course, I appear to have done something incorrectly. Yes. And in here, because I'm including that, when we encounter one of these ones, in addition to advancing the size of this, we also must advance an additional size, which is however much after we've gone past the render entry textured quads, we also have to go however many loaded bitmaps there were in our bitmap array. So the quad count times the size of a loaded bitmap pointer, right? As we advance forward. OK. So as you can see, not exactly a stunning success because we are not seeing our sprites. But that is the idea. And so now we just have to debug that. And I wanted to do it this way, like I said before, because I want to do it one step at a time. So now I want to just be able to debug one thing at a time, not have to debug both the aggregation part and the bundled part here. So you can see that this is calling the same path for all intents and purposes. So I just have to go debug now and see why I'm getting a difference between the two of them as we go. Now, I'm not crashing, so that suggests that the texture loading is at least loading out of a reasonable place. But yeah, we have to take a look and see whether these vertices are coming through in a reasonable fashion and everything else. And yeah, we'll take a look. We will take a look at that. I'm just doing a quick scan here to make sure I didn't do anything obviously wrong that jumps out at me. So anyway, the bitmap array at the entry +1, that is logical. Quad count being 1 is logical. We are opening our quads. We get 4 vertices out of it. And we are specifying the color UB as RGB and A there, which is exactly what I would expect it to look like. That all looks pretty reasonable to me. And these are set with the same values that I was having before. Again, looks pretty reasonable. So I'm going to go ahead in here, and I want to just take a quick look. I'm going to set a breakpoint inside the renderer to just see what those values are coming through as. Again, as just a sort of sniff test to make sure that when I see a quad, it seems like a sensible quad, and it isn't all messed up. So here's a bitmap. It's a pretty reasonable looking bitmap. So that's I could easily see that being something reasonable. In here we've got our vertices. Let's take a look at the hexadecimal. Kind of not particularly. Okay, those colors look super wrong. Ah. Yeah. Okay. I'm not quite right here. The RGB pack 4x8 call. I just realized I was a little overzealous there, wasn't I? So these don't multiply by 255. Right? They just unpack directly, right? So that's not particularly useful. You have to multiply by 255 first, right? You basically need to do that before you could actually use them. Oh my God. Okay, that's that's pretty good. I was not expecting that. I just realized that we didn't properly use we didn't. That was pretty good. Yeah, we did not use the proper value there. That was all right. That was funny. So okay, good. Just in time for the Q&A, we've finished what I wanted to finish, which is getting that set up and ready for us to move away from the fixed function pipeline. We've got some more work to do. We'll do that tomorrow, but I think that's a good place as any to stop. I'll go ahead and go to the Q&A here. Disused writes, emulating sRGB texture loads and sRGB fragment rates is not enough. sRGB also affects blending, which you can't emulate. Yes, that's true. In fact, emulation of sRGB, I also want to be clear, it's totally it's just a stopgap thing to do so that your game runs at all in a reasonable way. But it's not even correct because, again, sRGB, especially if you're using actual sRGB, is not a square and a square root either. So even just if you take blending out and you take bilinear out, right? Because remember, our bilinear will be wrong as well because the bilinear happens before the squaring. So this is just a kind of a patch that's like, okay, if your graphics card for some reason can't do this, then you can run through this pipe and will at least not look obviously completely wrong. But it's not at all the correct procedure. And I think you can even probably see, I mean, I don't know, I could be making this up, but I suspect that there's a dark fringe here that's darker than it should be. as well on the sprites, for example. And like just in general, you will have incorrect results if you are expecting to have our sRGB and your game is set up for it and you don't get it, then you have a problem, right? It's like there's no way to really fix it entirely that I know of anyway. So the rest code. Do you have a license for all those cubes? What do you mean? What do you mean a license? Rooktag, what texture will you use for rects and cubes? So for rectangles and cubes, those will all have textures eventually. We could use a 0 texture if we want to talk about solid color. But the cubes actually are supposed to be textured. They're just not textured right now because we haven't updated to a new art pack. But the cubes will have textures on them, like grass and stuff. MTS Mox, is it worth testing sRGB and MSAA in the non-OpenGL compatibility mode? I'm sorry, I'm not sure what you mean. What do you mean by in the non-OpenGL compatibility mode? Do you mean not setting the compatibility bit? If you mean not setting the compatibility bit, I'll just answer that before you actually have a chance to respond. But if you mean by not setting the compatibility bit, yes, it is absolutely worth testing it, but we can't test it yet because we haven't gotten rid of all the fixed function pipeline stuff. Once we've removed all the fixed function pipeline stuff, which is what I will be, what I'm working on getting us towards, then we can turn off compatibility mode. But at the moment, we can't because I'm pretty sure that OpenGL Core Profile 3 removes immediate mode. I could be wrong about that. Jim says, will you be using more than one shader program? If so, how do you minimize switching between programs when rendering? So at this point, I don't know that we'll have very many shader programs. We probably won't, but it really depends on the circumstance. One of the things that's true about rendering with ZBuffer like we are now is that we're not super dependent on the order of rendering. So if we want to, we can have some buckets, and when things come in, whichever shader they need, they just go into that bucket, and then we render each bucket with set the shader and render everything in the bucket. So we can certainly do something like that if we care. I don't know how many shaders we have. The other thing you can do is actually have branching in the shader. Sometimes if the branches are cheap enough, and since everything's always going through the same branch, you can actually just use shader branching if you have more fine-grained switching than that. MTS Mock said you could unset it and just see if the assert will fail. Yeah, we can. If you want to just see if it can get there, we can certainly try it. Yeah. So I think you have to specify core here. Is the thing. Let me look up this. That's the one we want. So we already have it. So I believe you would just specify that. And I guess if I was cool, I would probably do this. So now in theory, nothing will work. Okay, wasn't expecting that. Well, so yeah, I'm not sure why that allowed us to work at all, but I guess it did. So that's interesting. Because I would have expected the fixed function stuff to not work. Maybe they didn't remove it till 4? I don't know. I thought they removed it in 3. So I thought that would have errored. It might be that this driver just doesn't do the error checking properly. That's also possible. I have no idea. But that worked, apparently. So all right. All right, so now in theory, we're passing core profile bit. So that's good. And if we pass core profile bit, now we can just see over inside OpenGL. Let's see here. So it still errors out even in core profile mode. So I'm pretty sure this card just doesn't do it, or the driver doesn't know how to enable it, or something. Insofar as says, are you passing a major minor version too? I think the bit might be enabled sub 3.2. Well, we are. I mean, there's a minor version here. I can certainly pass 3.2 and see if that does anything. Right. Where is... So we did get the context. But still no dice. Yep. Looks like we're pretty much good to go now in terms of end of questions. So I'm going to go ahead and wrap it up. Insofar as I saw Insofar as join the chat, I will just end the stream. I wanted to ask you a question, so I'll be right back over to the chat in a minute here. But let's go ahead and wind this down. Okay. thank you, everybody, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org. It comes with a source code so that you can play around with it. We also have the forum site you can go to ask questions, a Patreon page you can go to if you want to support the video series, a schedule bot which lets you know what the schedule is going to be for the weekend, and an episode guide that lets you catch up on old episodes. Now, we also will be back here tomorrow, and as the schedule bot says, you can see here, this weekend schedule is 11 today, 10 a.m. tomorrow, but you'll notice here in the US, in the Pacific time zone, we have daylight savings time. It happens tomorrow. So actually, I believe that this will be at the same time tomorrow. Because basically what I did is I set them at the same time for the weekend, but the time zone changes over. So tomorrow, it will actually be at the same time, but it's actually an hour earlier because of the fact that the clocks go back. I think I did that right. I could be wrong and the clocks go the other direction. I have no idea. But either way, we'll be here at 10 a.m. Pacific Daylight Time tomorrow. So just be aware that the clocks do change if you're trying to make that broadcast. And I don't know, your time zone may not even have daylight savings time, in which case you'll be even more confused than I am. But there you go. So that's about it. I hope to see everyone back here tomorrow, assuming that the time change doesn't mess everybody up. Until then, have fun programming it, and I'll see y'all on the internet. Take it easy, everybody.